In this video, we're going to talk about a new type of function called an exponential function and their graphs. And so in our library of functions, we have the identity function, the squaring function, the cube root function, the squaring function, the cubing function, the reciprocal function, the absolute value function, the reciprocal squared function. We've already talked about properties of polynomial functions. And we've also talked about properties of rational functions. And so what we're going to do is we're going to add to the list in our parent functions, and we're going to go over their properties, exponential functions. And basically, exponential functions are functions of the form f of x equals a to the x. Notice that a, that is going to be a real number. Specifically, a is going to be a real number that is greater than 1. It's not greater than 1. I'm getting ahead of myself. It's going to be greater than 0. It's going to be a positive number. All right. It's going to be not equal to 1, and a is called your base, right? So there's going to be a number, and your variable is actually your exponent, which is why we call these exponential functions. And so an example of an exponential function is something like f of x equals 2 to the x, or f of x equals 0.3 to the x, right? Those are considered exponential functions. Sometimes you will see them written with the number in parentheses. Sometimes you will see it with the number not written in parentheses. The choice is yours as to how you want to write those. And so just so that we can get used to exponential functions, let's evaluate. Remember, in math, evaluate means to substitute a value in. And so I'm going to find f of -3. That means I'm going to, wherever I see an x in that function, I'm going to plug in -3. And so one thing about exponential functions, you have to remember your rules of exponents. For instance, if I have a negative exponent, I can make that exponent positive so that I can get the value of that number by doing its reciprocal. So this is the same thing as doing 1 over 4 to the third power, and 4 times 4 times 4 is 64. All right, and so basically what we found right here is an ordered pair. When my input value is -3, my output value is 1/4. All right, let's look at another exponential function. Notice here, this one is not a basic exponential function. This one is transformed, right? You see some transformations here, that +3, that multiplication by 2 out front, and that -9, that's a transformed exponential function. But what we want to do is evaluate this. Again, that's plugging in the value for the variable. So I'm going to have a 2 times 7. All right, -1 plus 3 is my exponent here, -9. Well, -1 plus 3 is 2, and 2 as the exponent on 7, that's 49. So that'll be a 2 times 49. 7 squared is 49. That's 98 minus 9, and so I'm going to get 89 as my solution there. But again, remember, this is a transformed exponential function. And so when I plug in -1, my output value is 89, right? And so that's another ordered pair if I were to graph that exponential function. Let's look at the graphs of these types of functions and their properties. What I'm going to do is I'm going to use a table of values so that we can get to some of the properties. I'm going to focus on this graph on the left, on f of x equals 2 to the x, right? And so I'm going to do me I'm just going to do me a chart. All right, I'm going to pick some x values, and I'm going to plug it into that function, and it's going to give me my y values. For instance, plugging in -2, that's 2 to the -2nd, right? Remember, that's 1 over 2 squared, and 1 over 2 squared is 1/4. 2 to the -1, well, that's 1 over 2 to the first power, so that's 1/2. 2 to the 0 power, oh, that's 1. 2 to the first power is 2. 2 to the second power is 4. So my ordered pairs on this graph here will be the point -2, 1/4. So it's going to go up a little bit. -1, 1/2. 0, 1. 1, 2. And 2, 4. Notice if I were to go to some more x values that are smaller than -2, for instance, 2 to the -3, well, that will be 1 over, that's -3, 2 to the third power, so that'd be 1/8, which is even smaller, right? So I have -3, 1/8. If I did -1 a -4, I get 1 over 16. If I did -5, I get 1 over 32, right? And so what my values are going to do, so my function, my values on the left side here are going to get closer and closer and closer to my x-axis there. And then here to the right, my y values are going to get larger and larger. And so I have a graph that looks like this. All right, and so for this f of x, g of x over here equals 1/2 to the x. Now notice 2 and 1/2 are very similar, right? Notice 1/2 is the same thing as 2 to the negative first power, right? Right, so I could write that way. And actually, when I have a power to a power, this is the same thing as saying 2 to the negative x power. So these graphs are actually related. Let's see how their graphs are going to look given that they are related, right? And so I'm going to use some of those same x values. I'm going to plug in, I'm going to go back to this original function, 1/2 to the negative second. Remember, if I want to make that exponent positive, then I do the reciprocal. The reciprocal of 1/2 is 2. So this is the same thing as 2 squared, which equals 4, right? And so I get 4 right there. 1/2 to the negative first power, well, that's 2 to the first power, which is 2. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2, and 1/2 squared is 1/4. And so what I'm going to get here is at the point -2, 4. I have an ordered pair, a point on my graph. -1, 2, 0, 1, 1, 1/2, 2, 1/4. And we have kind of that opposing relationship, so to speak. So we're going to have right in that line, and it's going to continue to go up on this side over here. All right. And so notice these graphs are very similar. Now, there are some properties about both of these graphs that we're going to talk about. For instance, the domain of both of these includes all real numbers, right? Negative infinity to infinity. The range of these two functions is x is greater than 0. There is never going to be a negative number, and these things would never equal 0, right? The graphs are smooth and continuous. So those are some nice properties when we try to do calculus. So it's smooth and continuous for all real numbers. When a is greater than 0, right? So remember we have f of x equals a to the x, right? So like the graph of 2 to the x, the function is increasing. When a is a number between 0 and 1, right? So a number like 1/2, the function is decreasing. They all have a horizontal asymptote. The line y equals 0. So in this graph, the line, my x-axis is my horizontal axis asymptote. And the same thing happens here because as we go to positive infinity, our graph gets closer and closer to the x-axis. And in this graph, when we go to negative infinity, our function gets closer and closer to our x-axis, right? So they all are going to have a horizontal asymptote. Okay, so we already know about asymptotes. And they all are one-to-one functions. All right. They're all one-to-one. They will pass the horizontal line test. Now, what we can do, this is for the basic exponential functions. We can graph exponential functions of the form f of x equals b times a to the x minus h plus k, right? Sort of like we did, sort of like this example up here where we had f of x equals this bad boy here, all right? For instance, there's the number that you subtract from your variable inside your function. So the inside of your function is actually in your exponent, all right? So the inside of your function is in your exponent. And so when we had a subtraction of addition or subtraction of a value from your x or to your x, that was a horizontal shift. When you multiplied a number on the outside of your function, like that b right there, that was a vertical stretch or a vertical shrink. And if you added or subtracted a value inside outside of your function, which is this is the inside, so this k is on the outside, you shift up or down. And so if I were to try to graph this function here, I would start with y equals 7 to the x. Remember, you try to take out all of the numbers out of your variable that are added or multiplied to your function, right? And so the most basic parent function is y equals 7 to the x. And then I work from the inside of the function, right? So we have y equals 7 to the x plus 3. That means we shift our function to the left 3 units. And then we have this multiplication by 2. So that's y equals 2 times 7 to the x plus 3. So I take that previous graph and I do a vertical stretch by a factor of 2. And then that last thing I do to that function is I subtract 9. And so if I want to get the full graph of this function here, I subtract 9 from all of my y values. I go down, I shift everything down 9 units, right? And that is how we can use transformations. And again, I take away that number that I'm multiplying, any addition and subtraction, and that gets me to my most basic function that I would start with, which is 7 to the x. Now, as we see in this graph, we have 2 to the x and the 1/2 to the x, and I've gone through that process to show you that g of x is actually the same thing, or can be written as 2 to the negative x, right? And so we've not talked about when there is a negative multiplied on the inside of your function. And this graph, these graphs here, kind of show us what happens. If I replace this x here with a negative x, right, then there's going to be a reflection about the y-axis now, all right? This is a reflection about the y-axis, meaning I make all of my x values negative to all of these points. So on this graph where I had the point 2, 4, if I do a reflection about the y-axis, then I have to negate my x-coordinate, right? And here I see that I get the point -2, 4. The same goes for this point here. On this graph, it's the point 1, 2. And so if I reflect about the y-axis, I negate my x-coordinate, and so you'll see that you get the point -1, 2. And this occurs for all of the points, right? And so replacing an x or multiplying the x by a negative value inside of your function means you're going to have a reflection about the y-axis. When it's on the outside, you negate your y-axis, and then as we saw from previous transformations, that's a reflection about the x-axis. One of the goals of this chapter or this section is for you to be able to solve exponential equations. There are multiple ways that we can do that. With the math and the functions that we know currently, what we're going to do is we're going to use what we call the one-to-one property to help us solve these exponential functions. And so since exponential functions are one-to-one, if I know that I have a base a to some exponent on one side of my equation, and the other side of my equation can be written with that same base, but maybe to a different exponent that may be a variable expression, then if this is going to be true, if a statement that looks like this is going to be true, the only way for it to be true is for these exponents to be equal. Because if the bases are the same and this is a true equation, then the exponents have to be the same, right? So then that means that x1 has to equal x2. Now, x1 and x2 are going to be algebraic expressions. It may be a constant, it may be an algebraic expression, right? So it's possible that these are I didn't want to say that, algebraic expressions. And so what we want to do is we want to be able to solve equations that have exponential functions. The hard part is that you have to remember your rules of exponents, because those are going to allow you to rewrite both sides of the equation as the same base to an exponent. Let's look at this example, right? If I'm going to be able to solve this equation, and I see on that left-hand side that I have a base of 3, then I'm going to have to be able to write my right-hand side with a base of 3. And so now I'm going to think about the powers of 3. Well, 3 times 3 is 9. If I multiply that by 3, I get 27. If I multiply that by 3, I get 81. And if I multiply that by 3, I actually get 343. Sorry, 243. And so if I want to write this side so that I can solve this equation, I'm going to have to write this 243 as 3 to the 1, 2, 3, 4, 5th power, right? And so now if my base on this side is equal to the base on that side, and this is a true equation, the way I'm going to solve this is I'm going to set, so I'm going to say by the 1 to 1 property, I know that 2x plus 1 equals 5, because if the bases are the same and these are one-to-one functions, then there's no choice but for these exponents to be the same, or this wouldn't even be an equation at all, right? And so I can solve this equation and I get x equals 2, all right? Now, since the domain of this function is all real numbers, I'm pretty confident that my solution is that. All right, let's go to this left-hand side of my equation B. Here I have square root of 2 to the x equals 1 over 16. Now I don't even see a base, right? But I do see 2 under a square root, and we should always remember that when something is when we take the square root of something, that's the exact same thing as raising it to the 1/2 power. So when I rewrite it as the 1/2 power, now I can see a base, right? And notice here, and it looks like 2 is my base. Well, if I think about powers of 2, well, 2 times 2 is 4. If I multiply that by 2, I get 8. And if I multiply that by 2, I get 16. And so I could write this 16 as 2 to the 4th power. Now, I don't see a base to an exponent like I did in this equation over here. I don't see it yet, right? But I see a power to a power, so I can use that power rule. So that would be 2 to the 1/2 times x. And here I have 1 over 2 to the 4th. I could rewrite that as 2 to the negative 4th power so that 2 won't be in the denominator anymore. Now I have a base of 2 on both sides of my equation. And so by the 1 to 1 property, I know that I could solve this equation by just equating the two exponents. So I have 1/2 x equals negative 4. I multiply both sides by 2, and I get x equals negative 8. All right. So that is how we generally solve these equations. What makes it difficult, once again, is the fact that you have to remember that you have to use your rules of exponents to get the same base on both sides. Right? But once you do that, the method is pretty simple to apply. All right, there are some applications that we want to get used to when we're dealing with exponential functions. Things in finance and in other areas, some things grow exponentially. And one of the things that grows exponentially is compound interest. Compound interest is when you invest money into an account, then the amount that you invest in the account is called your principal. And when you leave it in there, the bank or whatever financial institution that you're investing in, they'll say that they'll add on to your amount that you invest for keeping it in, for investing in there. They'll give you a premium by giving you a certain percentage. And so when we compound interest, and if you leave it in there long enough, you not only make money on the amount that you invest, but you earn interest or more money on the amount that you on the interest that you previously accrue, right? And so this is a compound interest formula. This A of t is the amount in your account. So it's the amount at time t. Some people call this the future value. If you want to know how much is in your account after t years have passed, then it's going to be on this side of this function here. P is your principal. This is the amount that you invest or put into the account. R is your rate, it's your interest rate. Now, it's usually given as a percentage, but when we do the calculations, we always change that percentage to a decimal. N is the number of times interest is compounded. And so, and T is your time, and time is always in years. And so, what we usually try to do is this form is used for dollar amount. So, you usually put a dollar amount here. Your interest rate is a percent, but you write it as a decimal. We're going to talk about what N is. Time is always in years, and then your output is a dollar amount, which is your future value, the amount in that account after T years have passed. There are traditionally different methods or a number of times that interest is compounded. Annually, that's one time of year, so that means n equals 1. Semi-annually is twice a year, so that means n equals 2. Quarterly is 4 times a year, so that means n equals 4. Monthly, that's every month, 12 months in a year, so that's n equals 12. And daily, that's 365 days. We even use that, I think, on leap years. And so let's look at an example where we get used to this formula. This is something that you have to memorize. A of t equals p times 1 plus r over n to the n times t. All right. So it says if $5,000 is invested in an account at an interest rate of 8% per year for 10 years, find the future value. So that's the amount after the time has passed if interest is compounded quarterly and in part B daily. So this is my P. This is almost like my R, but I have to change it to a decimal. And remember, you change it to a decimal by taking the current decimal, which is understood to be here, and moving it 2 places to the left. So that R is going to be 0.08. That's my T. And the word quarterly and daily gives us our N. So since it's quarterly, it's 4 times a year. And so that's N equals 4. So I'm going to place these values into my formula. I'm going to have A of 10 equals 5,000 times 1 plus my R, my N, to the N times T power. Okay? And so what I'm going to do is I'm going to get my calculator and I am going to put those values into my calculator. So that's 5,000. 1 plus 0.08 divided by 4. And I'm going to raise this now. You got to be careful here. If your calculator doesn't look like this, you need to open with a parenthesis and put your 4 times 10 there. Or you can just put 40. And I'm going to close my parenthesis. Now, I don't need the parenthesis here, but since I want you to be able to do it if your calculator doesn't look like this, sometimes the calculator you have may put this symbol on your calculator. And if you see that, then you definitely need to put that parenthesis around the 4 and times 10. So we get $11,040.20. And so I'll go ahead and say, so that's approximately $11,040.20. When it's daily, all right, the same stuff applies. The only difference is n equals 365 now. And so I get A of t equals 5,000 times 1 plus 0.08 over 365 to the 365 times 10. And when you put that in your calculator, you're going to get $11,126.73 if I round it to the nearest cent. All right, there is another way that interest can be compounded, and it's going to be even more times than daily. If you look here, you get much more money. I mean, in the grand scheme of things, it's not that much more, but hey, just by compounding interest daily, you get more money compared to only quarterly, right? And so what we want to do is we want to compound interest continuously. And so to do that, we need another exponential function. It's the number e. The number e is defined as the limit, right, as n approaches infinity of 1 plus 1 over n to the nth power, right? And so this is actually an exponential. This e is actually an irrational number, if I can get my word out. It's approximately 2.718, I think 2858 something, right? An irrational number is a number that's not a decimal. Sorry, it's a decimal, but it doesn't repeat and it doesn't terminate, right? It's almost like that number pi, or the square root of 2. Those are all irrational numbers. Now we know e is another irrational number, and its definition is based off of a limit, which is a calculus concept. All right, the basic natural exponential function is given by f of x equals e to the x. All right, and so when we use this, because a lot of things in nature actually compound continuously, or they grow continuously, or they may decay continuously. And when that is the case, we use this as our base instead of a formula like this that does it every certain amount of time. So every quarter or every month or every day. Some things change continuously, and that's what this function is for. And so when we talk about compound interest and calculating future value and all of that stuff, this is the formula. Some people call this the PERT formula. We still have our principal, but our base is no longer the 1 plus r over n to the nt. It's e, and our exponent on that e, which is our exponential function, is r to the t. And so we can determine if we put that 5,000 at 8% for 10 years, if the interest is compounded continuously by using this formula. So we're going to do a sub 10 equals 5,000 times e to the 0.08 times 10. And I'll show you how we can put that in our calculator. So I'm going to do 5,000. E is to the left of 4. If you do second ln, we're going to do e. If your calculator doesn't put this exponent here, make sure you open with a parenthesis. I'm just going to open up anyway. And I get 0.08 times 10. And I should get a little bit more money compared to that last example. And it's $11,127.70. And so I'll write this here. So that's approximately $11,127.70, which is slightly above the 126.73, 11,126.73 that we did when we compounded daily. All right, and any amount of money that you just can leave in the account and get more money is to your advantage. And so this concludes our introduction to exponential functions. We'll get to more solving of exponential equations a little later, but that's what we have here. And so I'll see you next time in our next video.